Hello, and welcome to the Chapter 2.3 Differential Equations lecture on first-order linear equations. So recall that an ordinary differential equation is said to be linear if it can be expressed in this form. And today we are only talking about linear first-order differential equations. And it turns out that all of these can be solved in a fairly algorithmic manner. A linear first-order differential equation is an equation that looks like this. So, in other words, the y prime, the dy dx, has only a function of x by it. It's not y times y prime, nothing like that. And similarly with the y piece, it has only a function of x by it. There's no e to the y times y, no y squared, nothing like that. And given an equation of this form, both sides can be divided by a 1 of x to put it in standard form. So doing so, it looks like this. And then we just rename this piece to be f and rename this piece to be p. And thus we can always put it in that form. This is the form that we'll want it in order to solve it. So let's consider this example, and we'll see the idea behind what we're going to do. The idea will be integrating factors. Step 1, we'll be putting it into standard form. Doing so makes it look like this. All we did here was, again, divide both sides by the leading coefficient. 2x over x squared is 2 over x, etc. And what we're going to do is multiply both sides by some function such that it is of the form f prime g plus fg prime. And then what we can do is undo the product rule. So I'll just tell you here how to do it for this particular problem, and then we'll see the general way. Let's multiply both sides by x squared. And then this equation becomes x squared y prime plus 2x y equals cosine x. And now here's the observation. This is now of the form where we call this f. This is f y prime plus, notice that 2x is the derivative of x squared. So this is f prime, where that's f, times y. Okay, but that looks like a product rule has been applied, and we can undo the product rule. So this is the same as f y prime. So that left-hand side is the same as x squared y all prime is equal to cosine of x. So that's our fy all prime. And look at that. Now we can solve this by just integrating both sides, and we'll have isolated y by itself. So now integrate both sides. By the fundamental theorem of calculus, integral of the derivative, they undo each other. And we have x squared y is equal to sine x, integral of cosine, plus c. And now dividing both sides by x squared, y is sine x plus c over x squared. And look at that, we found the general solution. So this is the idea behind integrating factors to solve first-order linear differential equations. We'll multiply both sides of the differential equation by some term that we'll learn how to find in such a manner that it becomes of the form fy prime plus f prime y, and then we can undo the product rule, and then it's just a matter of integrating, and then y is isolated. So how do we go about finding this integrating factor in general? Well, consider a general first-order linear differential equation in standard form, y prime plus p of xy is h of x. Then, if we multiply both sides by e to the integral of p of x dx, then it looks like this. Just multiply both sides by that. But now notice that the derivative of e to the integral of p of x dx is p of x times e to the integral of p of x dx. Because when we take the derivative of e to the power of something, well, e to the power of something is its own derivative, and then by the chain rule, we multiply by the derivative of the inside function, but the derivative of the integral of p of x is just p of x. So that's why this is the derivative of that. And voila, that's it. It's of the form that we want, where we can then undo the product rule. So now this is fy prime equals fh, And then we can integrate both sides, just like we did over here, and solve for y. So for any linear first-order differential equation, we get it into standard form, and this is our integrating factor, full stop. That's it. So here's finishing the derivation. That left-hand side is fy all prime, undoing the product rule, and then we integrate both sides, divide both sides by f, and we have solved for y. So, for example, what is the integrating factor for this equation? Remember that first, we need to always divide both sides by the coefficient of y prime to get it into standard form. So this is y prime plus 2 over x y equals x. And now that it's in standard form, we just take e to the integral of p of x. This guy is our p of x now. So our integrating factor will be e to the power of the integral of p of x dx, which is e to the integral of 2 over x dx. Integral of 1 over x is ln x. The 2 just hangs out there. We can pull it out. So this is 2 ln x. Okay, and technically there is a plus c there because it's the integral, but we can always ignore this. That's because it will cancel out on both sides after we multiply both sides by the integrating factor. You know, this is the same as e to the c once we use the exponentiation law. So it's like multiplying both sides by e to the c, it just cancels out. So we just don't even need to write it. So that's e to the power of 2 ln x. And now here's a common trick that we'll want to do. Whenever we have e to the power of something times ln x, well, we want to kind of isolate e to the ln x because they undo each other. So what we can do is apply the following exponential law. This is the same as e to the ln x all squared. That's because a to the b to the c is a to the bc. So we can just go this way in that. And the product up here becomes an exponentiation there. Okay, and now e to the ln x is x, so we have x squared. And now that we have that integrating factor, we can solve this differential equation by just multiplying both sides of the standard form of it by x squared and undoing the chain rule. So remember, we always want to use standard form, including when we're multiplying by the integrating factor, so dividing both sides by the coefficient of y prime. And now we found that the integrating factor, that was the x squared that we found here. So we multiply both sides by that integrating factor, and now it plays out pretty similarly to the first example that we did, distributing it's like that. And if you haven't made a mistake, it should now always be of the form fy prime plus f prime y, which is the same as fy all prime by the chain rule. So now this is x squared y all prime equals x cubed. And now we can integrate both sides. Integral of the derivative cancels out. Don't forget the plus c. And we have solved the differential equation by dividing both sides now by x squared. So that's the general method. And remember that if after you find the integrating factor, it is not of this form, then you have made a mistake. Because as we proved over here, this integrating factor will always get it into that form. And that's more or less all there is to integrating factors, really. And this method allows us to solve any first-order linear differential equation. Mind you, remember, many separable differential equations are not linear, so this method would not work for many of the ones that we could solve via separation of variables. And remember, what we're doing here is learning different techniques for solving first-order differential equations. Sometimes one technique will work where another technique does not. So you try your hand. Find the integrating factor for this differential equation and solve. Take a moment. All right, so first thing we always need to do is get it into standard form. Dividing both sides by 2, we have y prime minus 2y is 0. Now I want to point out that this could also be solved via separation of variables, and this can also sometimes happen. Differential equations could be solved by multiple techniques. But using integrating factors, we know that the integrating factor, that is e to the integral of -2 dx, which is e to the -2x. Remember, there's technically a plus c up here, but we can always ignore it. It cancels out. And then we multiply both sides by that integrating factor. In this case, the right-hand side is 0, so nothing changes when we multiply both sides by it. And now it is of the form fy prime plus f prime y equals 0. In this case, the f prime, that's the derivative of e to the -2x, which is -2 times e to the -2x. So that minus sign there is part of the f prime. It's plus minus that. So we have that. We integrate both sides. Remember, the integral of 0 is not 0. It's a constant. The derivative of a constant is 0. So we have that. And now we just divide both sides by e to the -2x. We have y as c times e to the 2x. Remember, the reciprocal of a exponentiation just puts a minus sign there, -2x. All right. Now we can also solve initial value problems. And remember that step 1 to solving an initial value problem is always first to find the general solution to the differential equation. The general solution to this is exactly what we found over here. All right, and then step 2 is to solve for that arbitrary constant. So we know that y of 0 is 3. Plugging in, y of 0 is c times e to the 2 times 0 is 3. E to the 0 is 1. So c is 3. So we have solved the initial value problem. And lastly, let's take a look at this differential equation. One of the points of this example will be reviewing how to do integration by parts. And also it's illustrating how we can solve a differential equation that we could not solve before. This differential equation we could have done with separation of variables. This differential equation is very much not separable. The right-hand side is not a product of a function of x and y, each only. It's a sum. But integrating factors work. First thing to do is to get it into standard form. Looks like that. And now, what is p of x? If you think p of x is 1, that's not right, because this is y prime plus p of xy. So be conscious of that. This is y prime plus -1 times y is x. So this is our p of x. So what's our integrating factor? Well, it's e to the integral of -1 dx, which is e to the -x. Plus e will cancel out, don't write it. So we multiply both sides by e to the -x. Distribute. And now it's of the form fy prime plus f prime y. As you can verify, derivative of e to the -x is -e to the -x. So we can undo the product rule, and this is e to the -xy all prime is x e to the -x. Undo that prime by integrating both sides. And we have this. Okay, we're just about done. We just need to remember how to integrate something like x e to the -x. And this is an integration by parts problem. Let's review how to do that. We'll often be needing it. Okay, so that's what we got. And here's how I always think about integration by parts. And this might be different from how you were taught it, but I find it a much nicer, more intuitive way to think about it and how to identify how to do it. So where big F prime is little f, and big G prime is little g, then here's what integration by parts says. It says the integral of big F little g dx is big F big G minus the integral of little f big G dx. So the new integral will have the derivative of one part times the integral of the other part. So if we can look at a problem and we can see that, okay, it has these two parts, and if I were to differentiate one part and integrate the other, would that make it an easier integral to solve? Then we have identified our big F and little g. And in this case, looking at this, we see, okay, if I differentiate x, it becomes 1, and integrating e to the negative x is easy as negative e to the negative x, and that's a much easier integral to solve. We've gotten rid of that x by differentiating it away. So in this case, that's integral of x e to the negative x. Okay, and that's big F, which is still x, times the integral of little g. Integral of e to the negative x is negative e to the negative x, minus the integral of derivative of x is 1, and integral of e to the negative x is still negative e to the negative x. And pulling out that minus sign, it's plus integral of e to the negative x dx. And as we anticipated, the reason we chose that big F and little g, it's now an integral we can actually solve. Integral of e to the negative x is negative e to the negative x. And don't forget the plus c, still there in integration by parts, of course. Okay, so with our integrating factor, we got this, and we found just now that the integral of that right-hand side is this. So we have e to the negative x times y is that. And now dividing both sides by e to the negative x, we get that y is negative x minus 1 plus c e to the x, better known as y is c e to the x minus 1. And we can always check our work by plugging in and verifying, and it does work. All right, so that does conclude integrating factors. The formula is not hard, and one of the main points of these examples was illustrating how to deal with simplifications like the e to the 2 ln x. You can pull out that 2 to an exponent, and other aspects like how to integrate the right-hand side, which will sometimes be more complicated integrals where we'll need to use integration by parts. So that's it. Have a great one.